Morning. Okay, in the last class, we discussed about the first unit, introduction to signals systems, properties of signals systems. Okay, and force system, time response analysis, and frequency response analysis. Okay, and natural response. All these things were discussed in our first class. Okay, now we are going to start the unit 2, that is the discrete Fourier series and Fourier transforms. What is meant by discrete Fourier series? You may have some idea about the discrete Fourier series. So here, let us consider the signal xp of n, which is a periodic signals of period of n samples. So that xp of n can be represented as xp of n plus ln, small n into capital N. Since xp of n is a periodic signal, it can be represented as a weighted sum of complex exponentials. Okay, weighted sum of complex exponentials whose frequencies are integer multiples of fundamental frequency 2 pi f or 2 pi by n. Okay, so xp of n is a periodic signal. It can be represented as a weighted sum of complex exponentials whose frequencies are integer multiples of fundamental frequency 2 pi by n. 2 pi by n. Okay, these periodic complex exponentials are of the form e power j 2 pi kn by n. It is of the form e pi j 2 pi kn by n is equal to e pi j 2 pi k into the small n is replaced by n plus ln by n. Okay, where l is an integer. Let it be treated as equation number 1. E power j 2 pi kn by n is equal to e power j 2 pi k into n plus ln, okay, whole by n, right? So since the discrete time Fourier transform of a sequence is periodic, when sampled, it consists of a finite number of distinct frequency components. When it was sampled, when it discrete time Fourier transform of a sequence is sampled, so it consists of a finite number of distinct frequency components. Okay, it means that discrete signals. Okay, if the number of frequency components is n, then the harmonics are given by 2 pi k by n, where k is equal to 0, 1 up to n minus 1. Now, any periodic sequence xp of n can be expressed as xp of n is equal to 1 by n into sigma k equal to 0 to n minus 1, xp of k into e power j 2 pi kn by n. So, any periodic sequence can be represented in discrete times in discrete form as 1 by n into sigma k equal to 0 to n minus 1 xp of k into e power j 2 pi k n by n, where small n is 0, 1 up to n minus 1. Let it be treated as equation number 2, where xp of k k equal to 0, 1, n minus 1 are called discrete Fourier series. This xp of k is discrete Fourier series coefficients. Okay, to obtain the Fourier coefficients, multiply both sides of equation 2 by e power minus j 2 pi by n into mn, and sum the products from n equal to 0 to n is n minus 1. So it is equal to sigma n equal to 0 to n minus 1 xp of n into e power minus j 2 pi by n into mn is equal to 1 by n into sigma n equal to 0 to n minus 1 sigma k equal to 0 to n minus 1 xp of k into e power j 2 pi by n into k minus m into n. So multiply this with e power minus j 2 pi by n into mn. That is equation number 3. So now these two summations are there, interchanging the order of summation on the right side of the equation number 3, so that sigma n equal to 0 to n minus 1 xp of n into e power minus j 2 pi by n into mn is equal to 1 by n into sigma n equal to k equal to sigma k equal to 0 to n minus 1 at xp of k into sigma n equal to 0 to n minus 1 at e power j 2 pi by n into k minus m into n. Here we are interchanging the order of the summation. So this will get we will get the equation number 4. Okay, we'll get equation number 4. Next, using the relation sigma n equal to 0 to n minus 1 e power j 2 pi by n into k minus m into n is equal to capital N if k minus m is 0 plus or minus n plus or minus 2n etc. or it is 0 otherwise, then we can substitute this in the above expression so that we obtain sigma n equal to 0 to n minus 1 xp of n into e power minus j 2 pi by n into mn is equal to capital xp of m. Now this is equation number 6. Now changing the order index from m to k, the Fourier series quotients xp of k in equation number 6 are obtained from xp of n by the relation xp of k, m is replaced by k. xp of k is equal to sigma n is 0 to n minus 1 xp of n into e power minus j 2 pi kn by n. Here m is replaced by this m is replaced by k. Okay, kn by n, that is equation number 7. So this equation number 7 and equation number 2 is referred as discrete Fourier series and inverse discrete Fourier series respectively. Okay, discrete Fourier series and inverse discrete Fourier series respectively. It is clear that both the sequences xp of n and xp of k are periodic with period n samples. So xp of n and xp of k, these are xp of n, this is xp of n, and xp of k, this is xp of k. These two are periodic with the period capital N samples. Therefore, discrete Fourier series of xp of n is equal to xp of k. Okay, discrete Fourier series of xp of n is equal to xp of k. Now we will see the properties of discrete Fourier series. So first property is linearity property. How the linearity property of discrete Fourier series is defined? It is considered. Let us consider the two periodic sequences x1 of n and x2 of n. Both are having the period capital N. So that discrete Fourier series of x1 of n is equal to x1 of k, and discrete Fourier series of x2 of n equal to x2 of k. Then it is defined as discrete Fourier series of a1 into x1 of n plus a2 into x2 of n is equal to a1 into x1 of k plus a2 into x2 of k. This is the linearity property of discrete Fourier series. Next, time shifting property of discrete Fourier series. If x of n is a periodic sequence with period n and discrete Fourier series of x of n is equal to xp of k, then discrete Fourier series of x of n minus n is e power minus j 2 pi by n into mk into x of n, where x of n minus m is a shifted version of x of n. Okay, so that is the time shifting property. Next one is symmetry property. Symmetry property is defined like this. If discrete Fourier series of x of n is x of k, then discrete Fourier series of x star of n is equal to x star of minus k, capital X star of minus k, or discrete Fourier series of x star of minus small n is equal to capital X star of k. Okay, and discrete Fourier series of real part of x of n is equal to discrete Fourier series of x of n plus x star of n by 2, or it is equal to 1 by 2 of x of k plus x star of minus k. Similarly, discrete Fourier series of imaginary part of x of n is equal to discrete Fourier series of x of n minus x star of n by 2, or half of x of k minus x star of minus k. So this is considered as odd part of x odd of k, and above one is x even of k. So where x of n is equal to x even of n plus x odd of n, where x even of n is nothing but half of the x of n plus x star of minus n, and x odd of n is equal to half of the x of n minus x star of minus n. Then discrete Fourier series of x even of n is equal to discrete Fourier series of half of x of n plus x star of minus n, or it is half of x of k, half of x of k plus x star of k. So this is nothing but real part of x of k. Similarly, discrete Fourier series of x odd of n is equal to discrete Fourier series of half of x of n minus x star of minus n, or it is equal to half of x of k minus x star of k. So it is imaginary part of x of k. So this is the symmetry property. And fourth property is periodic convolution. Periodic convolution. Let x1 of n and x2 of n be the two periodic sequences with the period n with discrete Fourier series of x1 of n is equal to x1 of k, and discrete Fourier series of x2 of n is equal to x2 of k, where x3 of k is x1 of k into x2 of k. Okay, convolution becomes a simple multiplication in frequency domain. Then the periodic sequence x3 of n with the Fourier series coefficients x3 of k is x3 of n equal to sigma n is m is 0 to n minus 1 x1 of m into x2 of n minus m. In summary, discrete Fourier series of sigma m equal to 0 to n minus 1 x1 of n into x2 of n minus m is equal to x1 of k into x2 of k. x2 of k. Now these are all the properties of DFS. So property sequence of period n and discrete Fourier series coefficients of period n. So this is x of n, this is x of k. x1 of n, x2 of n, this is x1 of k, x2 of k. So coming to the linearity property, a into x1 of n plus b into x2 of n, it will become a into x1 of k plus b into x2 of k. Similarly, time shifting property, x of n minus m will become e power minus j 2 pi by n into km into x of k. Frequency shifting, e power j 2 pi ln by n into x of n will become x of k minus n. Periodic convolution, sigma n equal to 0 to n minus 1 x1 of n in m into x2 of n minus m will become x1 of k into x2 of k. Okay, and multiplication, coming to the multiplication, x1 of n into x2 of n will become simple convolution. So 1 by m into sigma l equal to 0 to n minus 1 x1 of l into x2 of k minus l. Symmetry property, coming to the symmetry property, if we take the x star of n, this is x star of minus k, x star of minus n will become x star of k. So real part of x of n is xc of k, that is half of x of k plus x star of minus k. Imaginary part of x of n is equal to x odd of k is equal to half of x of k minus x star of minus k. So xc of n, x even of n, half of x of n plus x star of minus n will become real of x of k. X odd of n is equal to half of x of n minus x star of minus n will become imaginary part of x of k. If x of n is real, then x of k equal to x star of minus k. Real part of x of k is real part of x of minus k. Imaginary part of x of k is minus imaginary part of x of minus k. Mod x of k is mod x of minus k. Angle x of k is minus angle x of minus k. Then x even of n, x even part of n is equal to half of x of n plus x of minus n will become the real part of x of k. X odd of n is equal to half of x of n minus x of minus n will become the imaginary part of x of k. These are all the properties of our discrete Fourier series. Discrete Fourier series, properties of our discrete Fourier series. Next, coming to the discrete Fourier series representation of periodic sequences. Now, by doing a simple problem, you can understand this concept. So, determine discrete Fourier series representation for the signal x of n equal to cos n pi by 3. Plot the spectrum of x of n. Okay. So, by solving this problem, you can understand the concept. Okay. See, given the given the problem is x of n equal to cos n pi by 3. Okay, x of n equal to cos n pi by 3. Okay, cosine function. It is a cosine function. In the general form of the cosine function can be written as x of n equal to cos 2 pi f n. So the given function is cos n pi by. Equate these two by comparing these two equations. 2 pi f n equal to n pi by 3, or f equal to 1 by 6. T equal to 6. Look at period T or n equal to 6. Thus, frequency is the ratio of two integers, hence given cosine wave is a periodic signal. So, f equal to k by n, or it is equal to 1 by 6. N is 6, that is period. seconds is the Ka. We know that cos theta equal to e power j theta plus e power minus j theta by 2, or we can write this as cos n pi by 3. Cos n pi by 3 replace theta by n pi by 3. E power j n pi by 3 plus e power minus j n pi by 3 by 2, or we can write this as half of e power j n pi by 3 plus half of e power minus j n pi by 3. So x of n is equal to half of e power j pi by 3 into n plus half of e power minus j pi by 3 into n. We can write this as x of n equal to sigma k equal to n set of n summation n into c of k into e power j 2 pi n k by n, where sigma k equal to n indicates the summation over n number of samples. Since the sequence is periodic, then sigma n equal to 0 to n minus 1 will be same as taking summation over any consecutive n samples. Okay, so here n is given as 6. So we will take the consecutive n samples from -2 to 3. So 1, 2, 3, 4, 5, 6 consecutive 6 values. So consecutive 6 values are from -2 to 3. Taking summation over k equal to -2 to 3, that is consecutive 6 values. So that x of n will become sigma k equal to -2 to 3 c of k into e power j 2 pi n k by n value is 6. 2 and 6 cancel. So it will become e power j by k n by 3. Okay, so k is equal to sigma k equal to -2 to 3 c of k into e power j pi by 3 into k n. Okay, if k value is -2, similarly k value is -1, k value is 0, k value is 1, k value is 2, k value is 3. We'll substitute these values so that we'll get the expression like this: c of -20 e power j pi by 3 into 2n plus c of -1 into e power minus j pi by 3 into n plus c of 0 into e power 0 plus c of 1 into e power j pi by 3 into n plus c of 2 into e power j pi by 3 into 2n plus c of 3 into e power j pi by 3 into 2n. Okay, 3n pi by 2 into 3n. Okay. Okay, comparing the above equation and equation number 1, we find equation number 1 is, what is equation number 1? This is the equation number 1. So by comparing these two equations, we will get the values of c minus 2, c of minus 2 equal to 0, c of minus 1 equal to 1 by 2, c of 0 is 0, and c of 1 is 1 by 2, c of 2 is 0, c of 3 is 0. Other values of C of k can be calculated easily since C of k repeats after the period. So these are the values. Okay. Similarly, C of minus 2, C of minus 2, C of minus 1, C of 0, C of 1, C of 2, and C of 3 values can be calculated like this. Okay. Okay. This is the spectrum of class n by 8. This is the spectrum of class n by 8. Okay, next coming to the discrete Fourier transform. Fourier transform. So if we take the Fourier transform, it is used for frequency analysis of the signal. Fourier transform is used for frequency analysis of the signal. It is given by x of e power j omega is equal to sigma n is minus infinity infinity x of n into e power minus j omega n, where omega is frequency and it has the continuous range of 0 to 2 pi. Okay. So Fourier transform cannot be calculated on any digital process. Since omega is continuous in nature, this problem can be solved by evaluating Fourier transform at only discrete points of omega. So by evaluating Fourier transform at discrete points of omega, the total range of omega from 0 to 2 pi is divided into n equally spaced points, and Fourier transform is calculated at those points. It is called discrete Fourier transform. So it is divided into n equal interval uh, equal spatial points, and Fourier transform calculated these points only. Okay, the discrete Fourier transform omega is represented as omega k is equal to 2 pi n into n, 2 pi n by n, where k equal to 0, 1 up to n minus 1. Now, right? Now you will see the difference between DFS and Fourier transform, discrete Fourier series and Fourier transform. DFS, we take discrete Fourier series, is a Fourier series expansion of periodic discrete time signal. It is expansion of Fourier series expansion of periodic discrete time signal, discrete Fourier series. That is called discrete Fourier series. Next, Fourier transform converts periodic or non-periodic discrete time signal to frequency domain. Okay, it is converted into frequency domain, right? And then coming to the definition of DFT and IDF. DFT and IDF. So DFT, how it is defined? DFT is equal to x of k equal to sigma k n equal 0 to n minus 1 x of n into e power minus j 2 pi n into k by n, where k is 0, 1, 2 up to plus or minus n minus 1. So k indicates the index of the frequency. But coming to the IFD, inverse discrete Fourier transform, x of n is equal to 1 by n into sigma k equal to 0 to n minus 1 x of k into e power j 2 pi n k by n, where n is 0, 1 up to n minus 1. N is nothing but the length of the sequence, that is x of n. So both x of n and x of k both contains n number of samples. Okay, right? So this is about the definitions of DFT and IDF. Definition of DFT and IDF. DFT and IDF. Now we'll see. Now we'll see the Now we will see the problem. Find the DFT of the sequence x of n equal to 1, 1, 0, 0, and find the IDFT of y of k equal to 1, 0, 1, 0. Assume n equal to or length equal to 4. Okay, so x of k equal to sigma n is 0 to n minus 1. X of n into e power minus j 2 pi n k by n, k equal to 0, 1 up to n minus 1. Suppose if you take k equal to 0, for k equal to 0, x of 0 will become uh, x of 0 into e power minus j 2 pi 0 e power 0 by n. So e power 0 is 1 by n. K is 1, is like this. So you get x of 0, a 0, x of 0 equal to x of 0 plus x of 1 plus x of 2 plus x of 3. So that it will become 2 is 2. X of 1 is k is 1. Zero, 1, 2, 3. If k is 1, then x of 1 equal to sigma n equal to 0 to 3. 0 to x of n e power minus j 2 pi n k by n. So x of 0 into next x of 1 into, like this you can calculate, so that we will get 1 by 1 minus j. Similarly x of 2, x of 2 k is 2, k is 2. We will get x of 2 value is 0, k is 3. We will get x of k value is 1 plus j. So that x of k values are 2, 1 minus j, 0, 1 plus j. Similarly, you can calculate the idea of inverse discrete Fourier transform. Y of n is equal to 1 by n sigma k equal to 0 to n minus 1. Y of k into e power j 2 pi n k by n, where n equal to 0, 1 up to n minus 1. So here n equal to 0. Y is also 4 and n is 4. Y of 0 equal to n is 0. So 1 by 4, simply substitute these values. Y of 0 into e power j n value is 0, k value is also 0. Similarly, if k is 1 or n equal to 1, we can calculate these values. N equal to 2, we can calculate these values. And n equal to 3, we can calculate. So y of n equal to 0.5, 0, 0.5, 0, 0.5, 0, 0.5, 0. Right? Now this is another problem. Find the DSP of the sequence x of n equal to 1 for 0 is less than or equal to n is less than or equal to 2 and it is equal to 0 otherwise. So first bit is n equal to 4, n equal to 8, plot mod x of k and mod x of k, mod x of n and mod x of k. Okay, L equal to 3 here, length is given as 3 and n equal to 4, n equal to 4. The periodic extension of x of n obtained by adding use 1 0, that is n minus k 0, n minus 1 0, that is 4 minus 3 0 pattern. Okay, so x of k is n equal to 0 to n minus 1 x of n e power minus j 2 pi n k by n, where k is 0 1 up to n minus 1. See here, this is the sequencing problem. This is the sequence in the given problem. Periodic extension of sequence for n equal to 4. Periodic extension of the sequence for n equal to 4. Now x of 0 equal to x of 0 equal to now okay, see x of n is this one. So x of n into e power minus j 2 pi into n k by n. Okay, where k equal to 0 1 up to n minus 1. So this is x of n sequence in the problem. L is 3. So this is periodic extension of the sequence for n equal to 4. Okay, so x is 0, x of 0 equal to 1, x of 1 is 1, x of 3 is 1, x of 3 is 0. Okay, n is equal to 4, so x of k equal to sigma n is 0 to n minus 1, x of n into e power minus j 2 pi n k by n. So substitute the values of k equal to 0. If k is 0, then it is n is equal to 0 to n minus 1, 4 minus 1, that is 3. Okay, 0 to 3. Okay, so k is 0. Then substitute, then we will get x of 0 equal to 3. So here phase angle is also 0. For k equal to 1, by simply substituting x of 1, we will get 1, and x of the angle of x of 1 is equal to minus pi by 2. If k equal to 2, then x of 2 equal to 1, and it is 0. Okay, like that we will calculate the values for k equal to 3. So that we will get x of 3 is x of 3 is 1 and mod x of 3 is pi by 2. So magnitude is 3 1 1 1 and phase angle is 0 minus pi by 2 0 plus pi by 2. Okay, so that we can plot the magnitude and phase spectrums like this. So amplitude versus frequency, phase angle versus frequency spectrum of x of n for n equal to 4. This is the phase spectrum of the x of n for n equal to 4. Okay, the periodic extension of the sequence x of n for n equal to 8. N equal to 8. So in the above manner, we can calculate the same values: x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. N minus 1 is like this. Okay, so magnitude and phase spectrums. We can draw the magnitude and phase spectrums like this. Okay. So this is another problem. Determine the 8-point DFT of the sequence x of n equal to this one 1 1 1 1 1 1 0 0. Okay. Same manner we have to do the problems by taking the pen and writing on the paper only. We can understand the concept. Otherwise we can't do anything. Okay. So do it like the above problems. So do this problem as a homework. Find the find the 8-point DFT of the sequence x of n equal to 1 1 1 1 1 1 gen 0 0. Okay, by using this formula you can find out the DFT and IDFT also you can calculate. So IDFT can be calculated by using the formula. This is the IDFT. IDFT x of n equal 1 by n sigma k equal to 0 n minus 1 x of k into e power j 2 pi n k by n, where n equal to 0 1 up to n minus 1. Okay. 8 minus 1 7. So n is varying from 0 to 7. Okay. So for the 7 values we can find out the sequence. So we can get the sequence x of n equal to this one. Okay. So this is about the discrete Fourier series and Fourier transform. So with this I am concluding the today's class. So tomorrow we'll continue the same concept. Okay. Thank you.